Okay, hi everyone. So now we will talk about um, integrals of the form principal value f of x and then trigonometric, so cosine ax or a sine ax. Okay, so we did this a bit in class. So see class recording from week 11. We mentioned some lemma, and also look at the office hour by Andrian on Friday. So we use the lemma called Jordan's lemma. So let me prove it in this clip. Of course, you don't need to know the proof, um, but you need to know the lemma. Given two polynomials p and q with degree um, np, where is it? Um, nq is bigger or equal than np plus 1. So if you have that, then you look at the what we had, the semicircle, p over q, e to the iz. So that guy goes to 0 as r goes to plus infinity. Okay, so as you extend um, this semicircle, um, that the line integral, then the line integral goes to 0. Yeah. All right, so let's go with the proof. As usual, I first write in polar. So we write it in polar, and we have 0 to pi because it is a semicircle. We have r to the n, ein theta, and lower order terms. R to the m. Yeah, let me call it n and m, like in the book. 1 second. So this is m, and this is n. Okay. EIM theta, P0. So this is Q and this is P. And okay, then we have e to the I R EI theta times A. This is the EIZ term. And then d theta, yeah, so I R d theta. Okay, so that's the guy. All right, let's do our triangle. So triangle inequality for integrals. Rn EIN theta is 1, right? And that underneath we can't quite do triangle yet. So let me leave it as it is for a second with absolute value. Okay, EI R EI theta, and then just R. All right, good. Um, First, let me remove that stuff here. So why can we remove this? Um, so as R goes to plus infinity, this is a ratio of polynomials. Okay, and remember, um, so only the leading term matters. The the leading the highest degree matters. So this is the same as in real numbers. If you had xn and other stuff and xm plus 1, um, or let me say it this way, xm and xn plus 1, and you ask, okay, what's the limit of this as x goes to plus infinity? Well, this is, you can do L'Hopital, you can just look at ratios, whatever you like to do. This becomes xn plus 1 over xm. Okay, so that's what we're going to use here. Okay, um, right. So, right. So in the limit, what dominates from here is the highest order terms. So Rn plus 1 and then Rm. Okay, and we still have this guy that we haven't handled yet. We still need to take care of this term. Okay, so right, so yeah, we have this guy here. Now let's talk about this. Good. All right. So first, use Euler's formula, and on the top, so we have I R E I theta A is equal to what? Is equal to I R A cosine theta, okay, plus I R A I sine theta, right? But let me simplify this stuff for you. So this is R A sine theta, that's the real part, and then imaginary. Okay, so why am I splitting it like this? Well, because then what survives is just minus RA sine theta, because absolute value of this guy is 1. All right, so that's good. Um, okay, but now, so okay, for all practical purposes, what we have here is Rn plus 1 Rm, and then we have this integral. Um, Sine theta. Okay, now this guy is hard to integrate because of sine. There's a sine theta there. It's hard to find the antiderivative. Tough to find antiderivative. Okay, so what they do is the following trick. We know, so let me write the estimate. Right, so we know that sine theta is bigger than 2 over pi theta when theta is in 0 to pi over 2. Okay, all right. I'm gonna leave this trick to you that this guy, in fact, so let me say it here. If you use that sine, what is it? Yeah, sine pi minus theta is sine theta. You can show that this guy is equal to 2 times 0 pi over 2 and same integrand. So this is just a substitution like we did in the lecture. Okay, so now let's use the bound. Since we are in the right domain and we get minus RA 2 over pi theta. Well, okay, now this is easy. Now we can integrate this. We can find its antiderivative. So Rn plus 1, Rm, and then minus Ra 2 pi. And then we divide by minus Ra 2 pi, 0 to pi over 2. So, okay. So we can take out the R. That's all it matters. So we have Rm plus 1. And then we have 1 um, A2 pi. A2 pi. And then minus Ra A2 pi. Let me bring it out. Okay. So now take limit in R to infinity. What happens? This guy goes, this guy inside goes to 0. So this guy goes to 1, this factor. But what about this? Well, we assumed that m is strictly bigger than n. So we said this is bigger than n plus 1. So it's strictly bigger than n. Okay. Um, so yes, Rn plus 1, Rn plus 1 is equal to Rm minus n, which goes to 0. And that's it. That was it. Okay. Um, all right.